Hey everyone, and thank you for joining our podcast. So today we're going to review two of the sprints which we did in the last 4 weeks. So Nelson, please go ahead and let's start with sprint 13.
Hello, everyone. Thank you, Bailo. Yes, we have a lot to say during this sprint review because we did some nice work and we found some nice results. And we are still working on it, but I think we're going into a very interesting direction. So let's start talking about what we did during this the 13th sprint. Uh, let's. I think when I'm going to begin telling you that we find out a great collaborator, by the way, I have to say, and we're working on the solving the differential equations that we already find and we found in the field equations basically. And these field equations, of course, is complicated to solve. We have several variables or several functions that are unknown for us. For instance, you have the density, you have the pressure. I mean, talking about density, energy density, and also we have the form function, that the shape function of the bubble, which is roughly described what something we call the beta function there. So this function is quite interesting because basically you want to know how this function is going to evolve in time and how this function also is going to behave in space. So you have to give conditions on this function and also over the density and over the pressure. And this is not an easy task because for one side, we have some uh, properties that we know beta needs to have, which are very well known since Alcubierre's first uh, the article about warp drive. But about the density and the pressure, uh, it is quite open. I mean, it's almost any possibilities are okay. So we went on to basically two possibilities, and let me go very quickly on this. We have two cases. We're examining two cases. One case where we are looking for solutions that are time independent, and the other where we're looking for solutions that are time dependent. So in the scenario, when you have time independent solutions, what you find is that the field equations are uh, uh, tell you exactly what is going to be the relation between the density energy and the pressure. And it's a very interesting relation because it mimics very well a problem in cosmology where you obtain a specific, this is the equation of state, that's the relation. You obtain a definite equation of state, which is basically the pressure is minus the density energy. And it's quite interesting this. But this is something that is already there. You don't put it with your hand. The system is telling you this is what it is. So good. So we start working on that, and we found several nice results. Uh, Also, then we we say, okay, what about the time dependent case? And the time dependent case, it tells you, okay, you don't have a specific equation for state, but then it means that we have to tell what is it what we think is going to relate the pressure and the density. And we did. And we follow the most general thing that we can think of is a polytropic equation of state. In fact, it's what we call an extended polytropic equations of state. And it's, well, it could be quite complicated. It depends on some index, and depending of the value of this index, you are into different regimes of behavior of this fluid that is there. I mean, talking about perfect fluid, dust, and so on. So anyway, looking into these solutions, we solve it numerically. We're starting to find very nice results. The results are quite interesting. We start checking on that. But one of the most important things is that we obtain something that was somehow expected, some shockwave behavior somehow. So we have a motion of the bubble in time, and but there's some specific features that we are amazed is happening there, where it looks pretty much like a shockwave. And we expect that because some of the equations mimics, these are nonlinear equations, some of the equation mimics a bit like a Borger equations, which are used to describe shockwaves in fluids. But still, anyway, because we are putting a lot of things by hand, there is no way of not doing this to solve the differential system. uh, we're still checking on that. We think we have this and maybe another set of solutions that we are working on that right now. So in this scenario, we basically work on this, and we divide it into three cases. And you guys can see that we something that we call case one, which is the most simple of the cases. But we have case two and case three, where we just starting to complicate a bit more the problem, adding uh, less features to the problem, and also thinking in terms of when you have a cosmological constant, when you don't have anisotropies, when you don't have cosmological constant but you have anisotropies, and this already complicates a lot the problem. But okay, that's nice, that's very good, because that's what we're looking for, more complicated configurations of matter that maybe can tell us a bit more about what we can do with the system. So this is very exciting because we have a lot of things to say in the future, and we are really going ahead with this. We make a lot of other progresses that also still are open. We work a lot with the Lapse function. How's that? Well, you know, guys, that we have been telling you that we wanted to work with a Lapse function that enters into the metric. So you take into account the possibility of having time dilation somehow controlled by some function there. And between the observers, of course. But if you include this, what we found is like in the spherical warp drive metric, we found that it allows us to include heat, and heat in the form of heat fluxes into the system, which is very interesting, very, very, very interesting. And already including this into the energy momentum tensor is giving us a possibility of enrich more all the matter dynamics that you can include there. That's quite interesting. But also one thing that is very nice, like we put this Lapse function into the metric of Alcubierre, not only in the case of the warp spherical warp drive. And what we found is like the density at the end, the density energy is negative as we expect, but it has the Lapse function there. So if we can think in a way, physical way, or mathematical and physical way of how to absorb somehow these minus signs, in a sense, roughly speaking, there we can think of some configurations that basically will give you positive configurations, positive energy configuration. That's a huge thing. Of course, this is uh, a very previous result. I mean, but what we know is like, because the presence of the Lapse function is proportional to the heat fluxes, we know there are sure some thermodynamical relations that we can start digging in and trying to find if there is any possibilities for removing at least in some regions, removing the problem with the negative density energy. That's quite exciting. And this is only including the Lapse function. We are not thinking in terms of cosmological constant, anisotropies, and not even more complicated stuff like we can add, which are, for instance, electromagnetic fields and other approaches. I mean, this is just step one, let's say. So this is quite exciting, I think. I mean, we find out this, we calculate the energy conditions, and we find that this is quite exciting how it enters everywhere. Very nice. The other things that we did, we work a lot about something that is what happens to an object, but and goes very far. We're asking ourselves a question: if you have an object, a massive object, but an extended object, I mean a rigid body that is moving really fast, what are the effects that you find? So we start digging into that to see if there is some sort of connection between this and something that can link it be linked to the warp drive. So we found very interesting things. I mean, what happens to rigid bodies is not straightforward to think about it. You think about length contraction and tide dilation, and that's fine. But if you start going deeper, you see that this is a matter of how you measure. And it was quite interesting for us to learn that the final effect, in fact, discovered, I think first was by Penrose, is some sort of rotation, in fact, and it's quite amazing this effect in there. So now it means like you are moving very fast, and you have a like chip, and it's moving really fast. And for an observer that is outside, is going to see one side of the of the chip that is not seen as if we were uh, standing there. So you see literally like a rotation. The ray of lights are somehow curving, we can say, and it's quite nice this effect. How this is going to be related to the warp, we are not sure. But it was very good to go into this, and this is something that is open there still. But we wanted to work on many other things. This is we have a lot of open lines here, and we want to work on all of them and explore each of them.
Nelson, apologies. Let me say something about that.
Sure.
So this problem is very interesting because I'm not sure uh, how um, often we think about event horizons, but there are so many different kinds of event horizons. So we have event horizon for a black hole. We have event horizon when we have fast accelerating object, which is called Rindler horizon. And also when we have a bubble in space-time, it is going to also be covered by event horizon. And in relation to what you said about fast-moving object, what is going to happen is if we have object which is moving really fast, uh, it seems that the length is going to contract. But what is going to happen when we contract the length and the mass stays constant or even gets higher? So we're going to reach a state in which the object will be perceived as a black hole. So we're going to have some kind of event horizon. So because of that, we wanted to study this problem because we want to understand better the forming of event horizons, which we think it's useful for our warp drive research. And also, because I started talking, let me make just a few more points. So indeed, we reached a point in which our equations became very complicated. So I'm very grateful that we were able to find expert mathematician to help us with solving these equations, and we're really happy to work with him. And also thinking a little bit about the future. So right now, when we talk about warp drives, so we have mathematical solutions, but they're not physical. They're not physical, meaning that we cannot test them in lab. We cannot do anything with them. And there were some solutions which don't require negative energy. They say like the Bobrik solutions, for example, which require positive energy. But again, we cannot test them in a lab. So because of that, the direction in which we're currently going is to add new things into the warp drive matrix. We want to add angular rotation. We want to add heat dissipation. We want to add electromagnetic fields. We're going to add some specific quantum fields. And the reason why is that we can experiment with all these things in the lab. We can do angular rotation, we can change the temperature, we can create electromagnetic fields, we can create some quantum fields. So by enriching the warp drive matrix in this way, uh, it's going to be very useful for us because if we find solutions for this matrix which doesn't require negative energy because of all the reasons I just mentioned, this is going to be a solution with which we can start playing in a lab. And this is going to be very important because at the end of the day, we want to create something from the warp drives. And we think that this is the way. So Nelson, apologies for like taking some time. I just wanted to explain that. So please go ahead and continue with what you were saying before.
Oh, no, no, but that's very interesting because, as you said, there are several ingredients that we are start adding to the problem of the warp drive, and we're looking into that direction. And I mean, that's where we're pointing. Some testable forms of warp drive, and that's very interesting because, for instance, when you said quantum fields, the way that for other authors find a way to reduce the amount of energy into the Alcubierre warp drive, it was thinking in terms of a microscopic uh, warp drive, and how this the relation with the thickness of the warp drive is related with the amount of energy that is there. It's still negative energy, but anyway, they find a way that is somehow it's related to and it's a scale that is very small. And this is the kind of thing also that we're looking for at this for the moment. This is uh, things that we can try to measure in the lab. And it's quite interesting because I was about to say that we have several things that we can add, and things that are already people already did before, almost 20 years ago, even more. But this people work on different metrics with very simple type of matter configurations. And as it is, of course, they found what is correct. Some solutions that are not physical, that are not practical. But anyway, we believe that if we start changes the metric step by step, tuning here and tuning there, we might find some region of solutions that are testable in the lab, and that's quite exciting. I completely agree.
I
And
guess
one thing more, sorry, that I want to tell about the horizons. Uh, Indeed, the problem of horizon, this connection between the horizon is not simple, and that's what the question that I maybe I should put more emphasize more. This is if there is any connection between this type of horizon that appears when have an object that is accelerated, these Rinder's horizons, and even Unruh radiation, is this type of effects, are they connected somehow, or can we connect those with the warp drive? And this is a very interesting question for us, at least.
and I just want to point out that actually we had conversations with some of the universities we were partnering with. We're partnering with different universities, at least four of them. And in two of my conversations, they were really excited to start playing with the warp drive. So they offered their labs. So we definitely have a place where we can execute these ideas. So we're going to keep you posted, guys. But I just want to say, whenever we are done with enriching this warp metric with the equations we just mentioned, electromagnetic fields, heat dissipation, angular momentum, quantum fields, we'll be able to test it. So, Nelson, thank you. I think it was a great explanation, and I just scrolled to this part of the document where we are talking about the length contraction, and if somebody's interested, they can check the articles which are here. All right, so let's continue.
Yeah, you guys can look into that. It's a very nice article. I mean, this article and also the Raymond article, this is very exciting. I mean, if there is a red change in the shape, and the one from Penrose, I don't know if it's explicitly there, but it's is right there in the PDF. Anyway, if you guys want the articles, I think we can send the articles, and if you want uh, a copy of those. Anyway, this is for spring 13, and then for spring 14 we did a lot too. Uh, in this case, we still, of course, working on the cases that I mentioned before, the cases 1 to 3 of solving numerically the system of equations. And we have some preliminary results. I already told you about that, but we kept working on this. One of the things that I didn't told you before is I didn't tell you before. It's like we, in parallel to all this, we are uh, going, taking small step into the deep learning process of of solving problems in physics. We really want to understand. So we are following several steps that we think are the best ones, and solving simple examples like the one that you can see in here. That is the Borger's equation with five flow. But the point is like we are really working on the uh, step by step, uh, going into the next steps. I think we already told you about that, which is using some form of EI to work on all the possible solutions of Einstein's equations, and that can give us um, viable warp drive, viable in the sense that give us something that we want: positive energy, a small amount of energies, and so on. And that's something that we're doing every sprint. We add some task that is related to this. This is very important. So now let me go into the details of this sprint. In this sprint, we check a lot of things, but I think the more important things is like we start working on uh, the consequences of what happened with the energy conditions and the lapse function, which is basically a continuation of the work of the last spring. And here we concluded already that yes, we have something that is being added by the lapse function that is related to heat. And we look into the literature, and we indeed found that there are some works that relates negative lapse function with negative temperatures. And how this, what is the physical meaning of this? Well, you absolutely, you can have negative temperatures, and this is allowed. Of course, this is a local negative temperatures, but this is some things that are allowed in some regions. And then we're going to look into this to see what happens, because that's very exciting. So basically, this is going to is telling us, yes, guys, there is something here that we have to work on this. It was very exciting. And going into this, one other things that we did is like we start working on some beta functions to check of the warp drive metric. What are the forms that a beta function can have? Alcubierre's first work, he just proposed one form of the f function in his case. The beta function is basically the velocity times this f function. This is the shape function of the bubble, and he proposed one form of this function, but this doesn't have to be this. In fact, we don't even have to say which is what is the shape of this function, how this function is. You only need to give some conditions, which is basically telling that you need it to be flat, zero inside, flat outside, and allow that it has some curvature in the around the bubble. I mean, in the walls of the bubble. So we look into some constraints that we can find, some several beta functions that we can plug into the system of equations we are trying to work numerically, to see if we can make easier the work. And we did. But at the end, we find that it's better to leave the equations alone, and the equations are telling us more or less how to behave. Anyway, this is important because this is the beta functions tell us how the initial conditions are going to be, and how the boundary conditions are going to be, and that's very important to solve the problems of the differential equations. It's essential to even have solutions. You can have nonlinear equations, and you can have no solutions at all. So it's looking into the equations that exist and so on. It is a big deal. So we dedicate a lot of time to this and during this sprint. And another thing that is very interesting. This is an idea that is quite theoretical, but it's almost a curiosity, if we can tell. Is this approach. I mean, let's think about what we can call temporal warp drive. What is a temporal warp drive? We came with this idea. And I have to thank Zibailo because the discussions with him are really, really, really good. This if you think, there are several things to think about warp drive. But in all of them, what I think you can extract is like you have some displacement in one of the directions. And in directions, of course, I mean one of the coordinates. And if you are writing the metric in Cartesian coordinates, you have x, y, and z directions, but also the t, because it's part of the space-time. So we were thinking, well, what happens if you have like a not moving in the sense of not necessarily moving warp drive, not moving in space, but something like have some displacements in time. And that maybe sounds a bit strange, because you can think, well, you always have displacement in time. Well, that's true, but this motion is due to the fact that you have a parameter that you use to parameterize time. And then you, with that, you can just parameterize a geodesic, for instance, in some path. But what if you add something else to this motion in time? And this something else is the same type of deformation that is allowed in the x, y, or z directions. What happens if you add this to the Einstein's equations? And then we start looking into the, well, what would we need? Well, following the Bobrick approach to construct the warp drive, it is mathematical allowed to just do that, and we did it. And we found some equations, not that difficult. Luckily, of course, the most simplest configuration we can think of. We don't know what matter goes in. We have no idea yet. But what we know is like, in order to construct uh, correctly the connection between the observers inside and outside of the bubble, you think into a specific way of adding velocity. So one way is, we did all this only because we can do it easily in the spherical wheel drive. Um, if you do this, you see that you have the possibility of moving in the radial direction, but the velocity enters completely different in the metric, and also completely different in Einstein's equations. But the other thing is like, you can also have all the type of velocity we never think before about this. Even in the let's say regular warp drive configuration, which is allowing velocities that are angular. So you have motion in the other coordinates. And that's different, because this means there is no translation, a translation of the object, but there's some motion, and that we have some impact probably. It will have impact, of course, on Einstein's equations, and probably will have some impact about the energy conditions. We have to check about this. But anyway, in the case of the temporal warp drive bubbles, we managed to add this radial situation, and also we we made it for one of the angular coordinates, just one of them, to check out what is it. It wasn't that hard, and it's very interesting because the velocity there enters more or less in the same way that the radial velocity, but in other coordinate, of course. And it's quite interesting because it is dependent of the velocity of 1 over the velocity in a lot of places. And it means like if you have small velocities, the effect of this deformation of space-time that gives you the bubble is increased. But if you have larger velocities, you're somehow obtaining again flat space-time, like a static flat space-time. It's quite interesting. We still don't understand what are the physical implications of this, but we are exploring this, and we want to check out what does it mean to tell the metric move in time, the deform time instead of deform space. Apparently, what we obtained so far is like, okay, if you want to deform somehow time, well, you need to move anyway. You need some motion, and of course, probably you will need then some sort of matter there, which we still don't know how to add it, because there are we have to define correctly what are the observers here, and how these the velocities, basically we have to define the four velocities, correct four velocities for some type of observers that we can use to construct a proper energy momentum tensor for these observers. But this is a big deal. It's quite interesting. I mean, this is exploring theoretical stuff, but anyway, very, very interesting.
When we have the follow-up ticket for the temporal work metric, I guess we're going to take it the next sprint.
No, we have a here. It is is it 1553?
Oh,
Yeah.
oh, I'm sorry, you're right, you're right. So we
Yeah,
took it
yeah,
yeah, okay,
yeah,
excellent.
yeah.
So I feel this is a really interesting topic and question. So we're going to update you guys by the end of this sprint for our further development on the topic. Because you see, like from mathematical standpoint, we don't have anything which is stopping us to have motion in time, which sounds crazy, but mathematically it's correct. So we just want to explore what is going to give us. So we want to understand what is the matter configuration which theoretically is going to make this possible.
Yeah, definitely. Definitely, one thing is that we want to see is also what are the consequences of this? What are the physical consequences of this? Because this is uh, we are not. This is a train of thought that is different to Alcubierre's train of thought to construct the warp drive for superluminal motion. This is different. And it's quite exciting. I think, as a theoretical physicist, I really like this approach too. It's let's see where it's taking us.
So Nelson, I think that we have maybe one more ticket to discuss, or you're done with the sprint review.
I think we're okay because the other tickets are somehow all related, and I usually don't go on each ticket separately. I put all the together. So I think if you guys have any questions about what you have seen in the screen, just please let us know.
Excellent. And Nelson, I'm going to give one more update here. Usually during this course, we talk about the warp drive research, but in our company, AstrumDrive Technologies, we have several other projects going on. So we had a very big breakthrough with our electrical propulsion system about a week ago because we were able to successfully construct the first working physical prototype. So I know it sounds maybe a little bit crazy to say that we can have electrical propulsion system which works in space and doesn't create any type of exhaust. I mean, we can easily imagine that here on Earth because we have Teslas, right? But the reason why the Tesla car is moving forward is because we have friction between the tires and the road. If we put the Tesla car on a stand, it doesn't matter how fast the tires are going to rotate, the car is not going to be able to move forward. So we spent actually over 2 years of working with this electrical propulsion system which works in space. So this propulsion system which works purely and only on electricity. It doesn't have any exhaust. I mean, it has like some heat dissipation, but doesn't exhaust any gas. And we were able to finish our first physical prototype. We have very promising results, which we were able to measure. And now we started the second iteration of the electrical propulsion system, which we hopefully are going to finish between 3 and 6 months because we want to increase the amount of force the system generates. And after that, we're going to open it for the public because as of now, we, as a startup, operate more or less in a stealth mode. So I just wanted to give this update as well. And Nelson, before we close for today, is there anything else you want to talk about?
No, I think those news are great news. And please, guys, just check it out. Check out what we're doing about Warp Drive, and please, if check out the website of the company. It's great what we have in mind, and all the ideas that are always emerging from these works are amazing, and all the ideas that are also coming from your comments, which are being proving to be very helpful. I have to say. So thank you, everyone.
Yes, and we recently did some update on the website. I feel that it looks really great, so guys, please go and check it out. And having said that, thank you very much for listening, and let me wish to all of you to have a very nice and successful week.